Hey everyone, this is question number 9, and in this questions we'll discuss the concept of polarizability of an atom. So let's dive in. And so in this questions it is written, an atom of atomic number Z can be modeled as a point positive charge surrounded by a rigid uniformly negative charge solid sphere of radius r. The electric polarizability alpha of the system is defined by this, where this P is the dipole moment induced on applications of electric field E, which is small compared to the binding electric field inside the atom. It follows that alpha equals to. So we have to calculate what will be the polarizability after applying the external electric field. Okay. So, so this is the figure. In this figure, whatever in this questions it is written, I just represent the same thing in this figure. In questions it is written we have a atom with atomic number Z. So that's mean this atom will carry a positive charge Za, and it also carries same amount of negative charge because atom is usually neutral. So in this figure I have shown that this positive charge is placed at the center of the sphere of radius r, and the electron is distributed over the volume of this rigid sphere of radius r. Okay, so now the question says, if we turn on the electric field, external electric field, then what will be the polarizability of this atom? Polarizability of this atom. So I hope what has been asked in the question that is clear. So let's try to solve this problem. To solve this problem, let me already I have drawn here two figures. So this is case 1, this is the case 1, this is case 1, and this is case 2. Case 1 and case 2. So in case 1 we have this atom, and in this case there is no external electric field. That means we did not turn on any external electric field, so external electric field is 0 here. So if there is external electric field 0, then this positive charge will lie at the center of the sphere, and also this negative charge will be uniformly distributed over the sphere. So in this case, if we calculate the dipole moment of this charge system, that will be 0, because positive charge center and negative charge center, they will coincide with at the same point. So because of that, there will be no dipole moment, and that's mean there will be no polarizability. So alpha will be 0 in this case. So until you place the dipole external electric field, there will be no dipole moment. So alpha will be 0 in this case. But when we'll apply this external electric field, then what will going to happen? So now we are going to turn on the external electric field. So in this case, E not equals to 0. And let me draw this way, that we are going to turn on this electric field left right direction, left to right direction, like this way. Okay, left to right. So as soon as we'll turn on this external electric field, then what will going to happen in the atom? So that we can understood through this animation. So as soon as we'll turn on this electric field, you can see this external electric field will apply a force on this positive charge, and because of that force, this positive charge will get displacement towards a right direction, and electron also supposed to get displacement, but as it is written in the questions that electron will behave like a rigid sphere, so in this case electron will remain as it is. So in this case you can see now this positive negative charge center, the charge of the negative center, center of this negative charge lies at the center of the sphere, but because of this external electric field, positive charge got a displacement. The displacement. So if this displacement is d, then we can see that we can say that this now positive negative charge center will lies at the center of the sphere, but positive charge got a displacement d. So because of this system will behave like as a dipole. So there will be a dipole. So somehow if we calculate this dipole, we know the external electric field as it is written in the questions E. So if we divided this, let's say this is the induced dipole moment E, and then if we divided this induced dipole moment by this electric field, then we'll get the alpha. We'll get the value of alpha. Okay. And also one thing written in the question that this electric field is much lesser than the binding energy, binding electric field of this atom. Why it is written there? Because if we apply this external electric field which is much stronger than the binding energy of the binding electric field of the atom, then what will going to happen? This force on this positive charge will be much larger compared to the binding energy, and because of that this shape of the atom will completely destroyed. So we are not going to destroy the atom, we're just going to give a little bit displacement from this positive charge so that dipole is induced on the atom, and from there we can calculate what will be the alpha. Okay, so now to calculate this alpha, what we have to calculate? We have to calculate this dipole. So now how we can calculate this dipole? We have just use this definition. We know the atom is carrying charge Zd, positive charge Zd, and same amount of negative charge Zd. So Zd into this displacement d, but we don't know the displacement. So how we can calculate this displacement? So for that you have to ask another question, that why this positive charge will be raised at this position? Why it is not slowly just moving out from the atom? So that will not going to happen, because as soon as we'll turn on this electric field, so you can see there will be a positive because of this external electric field, there will be a force on the positive charge in this direction, and that force is Q into external electric field. What is Q here? Q is here Zd. Zd. And also you can see here, when this negative positive charge will get a displacement d from the center. So if we assume a sphere of radius d, so in this sphere will carry a uniform negative charge. So because of this charge, there will also be electric field, and that electric field will be actually acting towards the center of the sphere, and because of this electric field, let's say I am writing this as an internal electric field. So because of this internal electric field, there will also be a force, and that force again it will be Q into this internal electric field. So these two forces are actually opposite to each other. So after getting some displacement, so these two forces will be equal, and because of that this positive charge will be at rest, and that will be the equilibrium position. So to calculate this displacement, what we have to do, we have to equal these two forces. As soon as we'll make them equal, from there we can calculate the d, and once we get the d, then we can calculate the dipole moment, and we can get the dipole moment in terms of electric field, external electric field. So if we divided the dipole, induced dipole, by this external electric field, we'll get the alpha. Okay, to solve this, what we have to do, we have to again first we have to calculate the internal electric field at the position of the new position of the positive charge. So for that, what I am doing here, I am considering a imaginary sphere. Center is coincide with the atom, center of the atom, and radius of the sphere, let's say d. Radius of the sphere is d. So, and this sphere is carrying a uniformly negative charge, and what will be the charge density? The charge density rho we can write as Zd divided by volume of this atom. So it will be 4 pi r cube divided by 3, so we can multiply. Okay, so this negative, this small sphere carrying a uniform volume charge density rho, and this is the radius of the sphere is d. So using Gauss law, we can calculate what will be the electric field on the surface of this sphere. So what will be that electric field? So for that we can use Gauss law. So according to Gauss law, according to Gauss law, what we can write? We can write if the electric field on this sphere, small sphere is E. In this case, I have written En, so I am writing this En. Then En dot ds, En dot ds, closed surface integral is equals to Q enclosed divided by epsilon naught, divided by epsilon naught. So from there, what we can write, since negative charge is uniformly distributed, so we can write simply E in into 4 pi d square, and this will be equals to, here we write the volume charge density is rho, so rho into, but this is a negative charge because electron is there, so I can write a negative sign here, so rho will be in this case negative, so charge will be negative, so rho into, then this so rho itself is negative, and this is the magnitude of this rho. Okay, so rho into, then what will be the volume of this small sphere? Since charge is uniformly distributed, negative charge is uniformly distributed over the volume, so we can simply, what we can write enclosed as rho into volume of the sphere. So what will be the volume of the small sphere? It will be 4 pi d divided by 3, and then epsilon naught. So from there we can calculate E in is equals to minus rho 4 pi d square, 4 pi d square will cancel out, so 4 pi rho d divided by 3 epsilon naught. This will be the internal electric field, and this negative side indicate that if we write the direction, then it will be radially inward. It is going to be radially inward. So in this case, in this direction, radially inward. So now at equilibrium, so at equilibrium, what will be this net force on the positive charge? So there will be two force. One is Q into K internal, which will be radially inward, and equal to Q into I external, E external, which is radially outward. So these two forces must be equal to each other. So when you take this equal, what you can say, Q will cancel out from both sides. So what we'll get? We'll get E in is equals to E external electric field. So what is E already? If we put the magnitude of the E in, that will be ED divided by 3 epsilon naught is equals to E. So from there we can get D is equals to 3 epsilon naught into E divided by rho. Okay, so this is the D. So once we know the D, then we can write what will be the dipole moment. What will be the induced dipole moment? So therefore the induced dipole moment, induced dipole moment of the dipole is P is equals to charge, that is Q into D. Q into D. So what is Q here? Q is the Z into E, and D already we have calculated here. So write this value here, D. So what is D here? D is 3 epsilon naught E divided by rho. 3 epsilon naught E divided by rho. So now put the magnitude value of this rho. So what will be that? That we have already written here. Here. So if you put this rho, magnitude of rho here, so finally what you will get, Z E naught epsilon naught E divided by, so Z E and then divided by volume. So I am writing volume here. So it will be 4 pi r cube. Okay, 4 pi r cube. So here you can see this ZE will cancel out each other. This 3 will also cancel out each other. So what we'll get? We'll get the magnitude of the dipole moment is equals to 4 pi r cube into epsilon naught into E. Okay, so this is the magnitude of induced dipole moment. So now what we can do, add the definitions of polarizability. Therefore the polarizability of the atom is alpha is equals to induced dipole moment divided by external field. So if I divided this, what we'll get? We'll get 4 pi epsilon naught r cube into E divided by E. So again this E from denominator and numerator, they're going to cancel out. So finally we'll get alpha is equals to 4 pi epsilon naught r cube. 4 pi epsilon naught r cube. So this is the polarizability of an atom. Polarizability of an atom. And sometimes if you go to give your exam, like where you have to solve huge number of questions, more than 100 questions within 3 hours, so that time examiner simply asks this, what this alpha is proportional to r cube or r to the power n, then what will be the value of n. So from there you can see here that the alpha is actually proportional to the cube of the radius of the atom. So if we have more number of atomic number, that means radius will be more, and then polarizability of this atom will be more. If we have less number of atomic number, then radius will also be less, and in this case polarizability also be less. Okay, so I hope you understood this problem. See you in the next video. Thank you for watching.